All right, so going to talk more about some issues dealing with a review of bonding. And so I want to talk about now is the issue of, and I hope this is review for a lot of you, most of you, for all of you. This is the talking about hybridization. Hybridization. All right, and there are three hybridization states. There's the sp hybridization state, the sp2 hybridization state, and the sp3 hybridization state. Okay, so first of all, so I think maybe you're familiar with these, or I hope you are. Let's first of all talk about how we can predict the hybridization state of an atom. Prediction is that the hybridization state of an atom is going to be sp steric number -1. But if the atom has an unshared pair of electrons. So electrons takes an awful long time to write and to say, so I just abbreviate electrons with this symbol here. If the atom has an unshared pair of electrons that can be moved in resonance, then the hybridization state of that atom is sp steric number -2. So there's this drop down of hybridization state if the atom has an unshared pair of electrons that can be moved around in resonance structure. Okay, so first of all, let's review what exactly is the steric number. The steric number, right, and I'm calling that Sn, the steric number. This is the number of atoms, not the number of bonds, the number of atoms bonded to the atom of interest, because we calculate a steric number and we want to predict a hybridization state for every atom. It's the number of atoms bonded to the atom of interest plus the number of unshared electron pairs on that atom. All right, so this is the steric number. Maybe when you talked about this in Gen Chem, maybe you talked about, this is my, maybe when you talked about this in Gen Chem, maybe you had the term coordination number. And so that is a steric number and coordination number, they're the same thing. Okay, so let's look at some examples where we're calculating the steric number and predicting the hybridization state of this, that, and the other atom. All right, so let's start out with something pretty easy, like for example, the water molecule. So there's the Lewis structure of the water molecule. What is the hybridization state of the oxygen atom in water? Well, I hope we know since high school maybe that it's sp3. Okay, but how are we coming up with that based on this prediction of hybridization? Okay, so the steric number of this oxygen atom, it is bonded to two other atoms, two hydrogens, and it has two unshared electron pairs on it. So its steric number is equal to 4. And so that means we have a prediction of hybridization of sp3. So it's the steric number -4. minus 1, unless the atom has an unshared pair of electrons that can be moved around in resonance, but we're not going to talk about that just yet. We'll get to that later in the lecture. Okay, so now remember that we said yesterday that showing these unshared pairs is totally optional. So this is going to be a problem for many people, because I never have to show you an unshared pair of electrons. You need to know that they're there. Okay, so let's do another calculation of hybridization state. So maybe something like tell me what is the hybridization state of the oxygen atom. Okay, and give me the answer here on the chat. What's the hybridization state of this oxygen atom? Anybody? Oh, okay, so I see someone says sp2, sp2. Okay, great. All right, so now where are we coming up with that? All right, so this oxygen atom, it's a steric number. It has 2 unshared pairs of electrons. Its steric number is equal to 3. It's bonded to one other atom. It's bonded to a carbon atom, and it's bonded to, and it has 2 unshared pairs of electrons, steric number of 3. And so that means hybridization prediction is sp2. What about this carbon atom right here? What is its prediction of its hybridization state? Well, that is also going to be sp2, is it not? Because that carbon atom is bonded to 3 other atoms. It has 0 unshared pairs of electrons. 3 plus 0 is still 3. So that's a steric number of 3. And so that's an sp2 hybridization state. Okay, so now what about the nitrogen atom in hydrogen cyanide? What's its hybridization state? Anybody here on the chat? What's the hybridization state of the nitrogen atom? Okay, all right. So I see a lot of people telling me sp, that's correct. So there's an unshared pair of electrons on this nitrogen. It's bonded to one other atom. It has 1 unshared pair of electrons, steric number of 2. So that means an sp hybridization. And what about this carbon over here? What's its hybridization state? Well, that's also going to be sp, because it's bonded to 2 other atoms. It has 0 unshared pairs of electrons, steric number of 2. That's an sp hybridization. Okay, so this is how we predict hybridization state, unless the atom has an unshared pair of electrons that can be moved around in resonance. We'll get to that later on in the lecture. Okay, so now let's just review what the hybridization states look like. Okay, now I see people are sending me questions over the chat. I'm going to lecture for about 50 minutes, and then I'm going to try to deal with the questions. I can't stop the lecture to entertain questions on a regular basis, because I'll just never get through the material. So I thank you very much for your questions, but let me, if I don't answer them, it's not because I'm a jerk. It's just I have to get through this material. Okay, so I'll end a little bit early, and then I'll try to deal with some of these questions. Okay, so now let's talk about what these hybridization states look like. The sp3 hybridization state, the atom is imagined to be at the center of a regular tetrahedron, right? Tetrahedron is a pyramid with a triangular base, and the sp3 hybrid orbitals are directed to the vertices of that tetrahedron. Okay, and so this is what the complement of 4 sp3 hybrid orbitals look like. Now, that's very well and good, but lots of times we don't want to take time to draw these orbitals, right? Because remember, there are two theories of bonding, the molecular orbital theory and the valence bond theory. The molecular orbital theory uses these orbitals, and the valence bond theory uses the Lewis structure. So most of the time we're going to be using the valence bond approach. And so instead of drawing these molecular orbitals, we want the Lewis structure version of this hybridization state. And so what we do is we imagine the atom, I'm going to put a little dot, and now to portray the geometry, the tetrahedral geometry of the sp3 hybridization state, to portray that on a piece of paper or on a computer screen, what we do is that the sp3 hybridized atom is imagined to be sitting at the center of a complement of 4 bonds. 2 bonds are in the plane of the paper and would be represented by solid lines. 1 bond is jutting out toward you, and it is represented on a wedge, and the fourth bond is pointing away from you and is represented on a dash. So this is something that we're going to be seeing repeatedly, which is this dash and wedge representation, right? So it's 2 solid lines representing bonds in the plane of the paper, a dash and a wedge. The wedge is a bond pointing out at you, and the dash is a bond that's receding away from you. Now, I could have put the 2 solid lines in a different location. I could have wedged it over here. I could have dashed it over here. However you do it, this dashing and wedge portrayal of the sp3 system has to look like what? Like a chicken foot, right? Like a tetrahedron, where that is the leg and these are the 3 toes, right? So I assume that most of you are maybe hipsters from New York. Maybe you've never seen a chicken. I grew up on a farm, so I've seen plenty of chickens. Maybe you know what a chicken foot looks like. Well, so when we're drawing this dash and wedge of an sp3 hybridized atom, we want to draw this tetrahedron accurately so that it looks, so it kind of looks like a chicken foot with a leg and 3 toes. Okay, so another way, people get hung up about, like, does the solid line have to be there? The solid line have to be there? No, it doesn't. It could also be, I could also have done something like this. I could have put, 2 solid lines in the plane of the paper, a dash, and a wedge. So that's also acceptable, although it's not as pretty as the one I drew before. 2 solid lines, a dash and a wedge, try to make it look like a chicken foot. Okay, the sp hybridization state, well, the sp hybridization state is that we have an atom, and the atom sits at the center of, before we go, let me go back to this sp3, is that, let's remember maybe from Gen Chem, that these angles are about 109.5 degrees, something like that. Okay, the sp hybridized atom sits at the center of a complement of 3 sp2 hybrid orbitals, and then there's an unhybridized p orbital. Okay, so that's what the sp2, the arrangement of orbitals for the sp2. And again, we want to illustrate an sp2 hybridized atom on a piece of paper or on a computer screen. We don't always want to write orbitals. And so how this is done is that we recognize that the sp hybridization state is trigonal and it's planar. And there are a couple of different ways of showing an sp2 hybridized atom on a piece of paper or on a computer screen. So let's look at this guy here, right? That's sp2 hybridized oxygen and sp2 hybridized carbon. Great. So how would we draw this? how would we draw this on a piece of paper or on a computer screen? A couple of different ways. One way would be to draw it like this, right? But here, this is what I'm calling face on. You're looking at the molecule is standing up in front of you. You're looking at it sort of face to face. And these angles here are about 120 degrees. These angles are about 120 degrees. The other way of looking at sp2 hybridized atom would be on edge, where I've taken this molecule and instead of looking at it face on, now what I'm going to do is I'm going to look at it on edge. And so when I do that, I see this hydrogen is now on a wedge because it's pointing at me. This carbon and this oxygen, they're on solid lines. They represent atoms on the plane of the paper. And then I have a dash back there. That's the other hydrogen, right? So this is on edge. So these are two ways of drawing sp2 hybridized atom. It can either be face on. This is usually what we do, but we can also draw it on edge where we're looking at that molecule just from a different perspective. All right, finally, the sp hybridization state. Well, this is linear. So these molecule, this carbon atom and this nitrogen atom over here, they're both sp hybridized. What does the sp hybridization state look like? This is hard to draw. It's going to just look like a daisy. And so there are two sp hybrid orbitals, and then there's an in and out. There's an in and out unhybridized p orbital and an up and down unhybridized p orbital. And to represent the sp hybridized atom, since it's linear, we can just imagine putting that whole molecule on our plane of the paper, and so everything is going to be a solid line because it's because the solid lines represent bonds in the plane of the paper. Okay, so this is how we represent the various hybridization states. Okay, so now we talked about exceptions to the prediction of hybridization, which is occasioned by resonance. So what I want to get into now is talking about resonance structures, drawing resonance structures and the meaning of resonance structures. And maybe you got some of this in Gen Chem, but we need to go way much farther in when we talk about resonance in organic chemistry, because it is an extremely important idea. Okay, so first, how about let's do another, let me return to this piece of paper here now. Let's do some more practice problems on prediction of hybridization. All right, so there's the condensed formula for this molecule. Tell me the hybridization state of everything. What's the hybridization state of the carbon? What's the hybridization state of the nitrogen? What's the hybridization state of the oxygen? So there's a condensed formula. Now we're predicting hybridization state based on the number of atoms and the number of unshared pairs of electrons. So probably what you want to do is draw the Lewis structure on a piece of paper, or maybe if you, if you can imagine it. Okay, so the Lewis structure would be the carbon atom is bonded to 3 hydrogens. And now carbon forms 4 bonds when it's neutral. Nitrogen, that it's neutral. Nitrogen forms 3 bonds when it's neutral. Oxygen forms 2 bonds when it's neutral. What about unshared pairs of electrons? Well, all of these atoms like to have an octet usually. So just filling in all of the unshared pairs of electrons, we would get something that looks like this. And now let's just say resonance is not involved here. We'll get to that in a minute. And so this nitrogen has a steric number of 1, 2, 3. Steric number of 3. And so that's an sp2 hybridization. And this oxygen atom over here has a steric number of 1, 2, 3. And I'm telling you that resonance isn't in play here. So that would also be sp2. Right? So did we get all of that? Yes? Okay. How about let's draw a dash and wedge picture of this molecule now. Oh, I forgot about this carbon, right? Steric number of 4, that's sp3. So now what if I wanted to draw a dash and wedge picture of this molecule? What would I come up with? Well, here's the carbon atom, and he's sp3 hybridized. And so that means 2 solid lines representing bonds in the plane of the paper, a dash and a wedge, and so I'm going to put 3 hydrogens here, and I'm going to put a nitrogen here. Where do they go? It doesn't matter, but let me tell you something in case you didn't know. Looks are everything, right? I'm going to try to draw this in a way that where the molecule makes visual sense and is beautiful to look at, right? Hate to tell you this, looks are everything. Okay, so maybe I'll put the hydrogen there, a hydrogen there, and a hydrogen there, and a nitrogen there. This nitrogen is sp2 hybridized. So that means this sits at the center of a complement of something that looks like a little Y, or an upside down or right side up Y. And so I'm going to maybe put the oxygen up here like that. And so that would be a very nice 3D drawing of the molecule. And now remember, showing unshared electron pairs is totally optional. If I wanted to, I could put a line here terminated by an unshared pair of electrons. I'm not going to do that. If I wanted to, I could draw a line up here terminated with an unshared pair of electrons. I'm not going to do that. If I wanted to, I could draw another line over here terminated by another unshared pair of electrons. I'm not going to do that because drawing unshared pairs of electrons are totally optional, and I'm just choosing not to do it. Okay, so that would be the dash and wedge picture of that molecule, and it is supposed to convey a nice 3-dimensional flavor to the structure, which this CH3NO does not. So now maybe in Gen Chem you talked about molecules that are linear, planar, tetrahedral, bent, right? Remember all of that? Yeah, well, you know, that was then and this is now. Is that those one-word descriptions apply to very few molecules. So what about this one? Is he linear? No. Is he bent? No. Is he tetrahedral? No. What is he? He's none of those, right? Those one-word descriptions that you maybe learned in Gen Chem, they're applicable to some kinds of organic molecules, but most organic molecules have too many atoms, too many bonds. There's too much diversity of geometry to be able to classify everything into those one-word descriptors. Okay, so let's talk about resonance. What is resonance? Resonance is the ability to draw alternative Lewis structures for the same molecule. So we have all of these rules about drawing Lewis structures, but we'll see that for many molecules, we can come up with more than one Lewis structure. Okay, so let's see. I'm looking at my cheat notes here. I have to get my data, so just bear with me for a second here. Here you are. Okay, so if we can imagine the thiocyanate ion, and so that is SCN minus, right? Carbon is the central atom. And so if I wanted to draw a Lewis structure of SCN, what I could do, oh, okay, instead of SCN, let's do OCN. Yeah, OCN minus, right? Because just oxygen is more important. All right, so oxygen forms 2 bonds when it's neutral and has an octet of electrons. Carbon forms 4 bonds when it's neutral and has an octet of electrons. And nitrogen forms 2 bonds when it has an octet and has a negative charge on it, right? So I'm coming up with a Lewis structure of OCN where where I've satisfied the valencies of everything based on that table that I gave you yesterday. All right, so now if I wanted to draw in the unshared pairs of electrons, I would come up like that. Okay, so this is a nice Lewis structure. Everything has the right number of bonds. Everything has an octet. Everything has the formal charges represented. Great. But I can draw another Lewis structure, which would also be correct, which would also be OCN minus. I could put the negative charge on this oxygen. When oxygen has an octet, and remember, most of these atoms, most of the times are going to have an octet. When oxygen has an octet, it forms 1 bond and has a negative charge on it. Carbon forms 4 bonds when it's neutral, and nitrogen forms 3 bonds when it's neutral. Well, there's another perfectly okay Lewis structure of OCN minus. Okay, these 2 guys, these are resonance structures, and their relationship to each other is indicated by this double-headed arrow, right? These guys are resonance structures. And let's remember that their relationship is indicated by this double-headed arrow, not an equilibrium arrow, not an equilibrium arrow. Okay, so what exactly do resonance structures mean? It turns out, so this is what a resonance structure is. It's an alternative Lewis structure for the same molecule, but the meaning of resonance structure, is that the actual structure of the molecule, of the ion, whatever it is we're looking at, the actual structure is a composite of all its resonance structures. Okay, so if we look at these resonance structures here, I believe this is called isocyanate. If you look at these 2 resonance structures for the isocyanate, there's immediately a crisis. So this oxygen is bonded to the carbon, but this resonance structure is saying that it's a double bond between the oxygen and the carbon. This resonance structure is saying it's a single bond between the oxygen and the carbon. So which is it? This resonance structure is saying this nitrogen is bonded to the carbon by a double bond, but this resonance structure is saying that the nitrogen is bonded to the carbon by a triple bond. So which is it? Which is the correct description of bonding in this isocyanate ion? Well, what resonance is telling us is that the actual structure of the molecule is neither this one, nor is it this one. It is a composite of the two resonance structures. So this is what is called the resonance hybrid. And so, so this oxygen atom is bonded to the carbon, but that's not really a double bond. It's in another perfectly legitimate resonance structure. This bond is a single bond. It's not a double bond. It's not a single bond. It's somewhere in between being a double bond and a single bond. So we represent that in the resonance hybrid with maybe a dotted bond there. This means it's not a single bond. It's not a double bond. It's somewhere in between a double bond and a single bond. What about this carbon bonded to this nitrogen? This resonance structure, perfectly good resonance structure, is saying it's a double bond. This perfectly good resonance structure is saying it's a triple bond. So which is it? It's neither of them. The bond is somewhere in between being a double bond and a triple bond. And so we represent that in this way, where we know it's at least a double bond, but that triple bond, that's kind of iffy. So we're going to draw that third bond with that dot. Okay, now there's another crisis to deal with here, and that is the location of the negative charge. This resonance structure is saying the negative charge resides on nitrogen. This resonance structure is saying the negative charge resides on oxygen. So which is it? Is the negative charge on oxygen or on nitrogen? It's on both of them at the same time. The actual structure of the molecule is a composite of its resonance structures. So, and the way we illustrate that would be the lowercase Greek letter delta minus. That means partial negative charge on that oxygen, right? The oxygen in one resonance structure is negative charge, but it isn't in the other. So in actuality, it's just partly there. And also a delta minus on the negative, illustrating a partial negative charge on the oxygen. This thing here, this is called the resonance hybrid. And it is, or it purports to be, the actual structure of the molecule. So OCN minus never looks like this. OCN minus never looks like this. The actual structure of OCN is this, where these double bonds or triple bonds are partial bonds, and where the negative charge is actually spread out over the whole molecule. Okay, so this is kind of a challenging concept to think about, that the actual structure of the molecule is a hybrid composite of all of its actual resonance structures. So let me show you some pretty pictures here. Try to anyway. The whole idea of a hybrid. What do you get when you cross a horse and a donkey? Anyone know? Anyone here not a hipster from New York, maybe? Oh, you get a mule, exactly. Oh, look at that. Okay, well, did you guys grow up on a farm? That is a resonance structure. This is another resonance structure. But when you cross a horse and a donkey, you don't get something that is flipping back and forth between being a horse 1 minute and a donkey the next minute. you get the hybrid, which is a mule. And what you want to notice is the hybrid has characteristics of both parents. It has the magnificent stature of a horse, but a mule is not a horse, and a mule isn't a horse sometime and not a horse another time. It's its own animal. It has the long ears and stubborn disposition of a donkey. But the mule is not a donkey, and it's not flipping back and forth between being a donkey and being something that's not a donkey, right? This is the hybrid. This is the thing with all those dotted lines and the partial charges. This is the actual structure of the molecule. But the resonance hybrid is unwieldy to draw, so frequently we resort to the actual resonance structures. Okay, so let me ask you another question. What do you get when you cross a goat with a lion and a dragon? Right? These are the resonance structures. These are the guys that have the charges and the bonds and whatever. But when you combine all of these three, what do you get? Anyone have the answer here? Oh, a chimera, a Galigon. Ooh, never heard of that. Okay, yeah, you get a chimera, something that looks like that. See, this is the actual structure of the molecule. It's not a goat, it's not a lion, it's not a dragon, and it's not flipping back and forth. One instant it's a goat, another instant it's a lion, another instant it's a dragon. That's not what resonance is about. The actual structure of the molecule is a composite of all of its resonance structures. Okay. All right, so let's, okay, so that is what a resonance structure is, and we talked briefly about the meaning of resonance structures. Now let's get into some nitty-gritty about writing resonance structures. Okay. So rules for resonance. Okay, so when you are writing a resonance structure, so what I'm going to do is just going to lay down the law here, just like give you all of the rules, and then we can talk about, and then we can work a bunch of examples. Okay. When we're writing a resonance structure, what we're doing is you move electrons. You move electrons in p or pi orbitals. You never you never move atoms, right? Because remember, resonance structures are saying something about the same molecule. Resonance structures are alternative Lewis structures of the same molecule. If you're moving atoms around, what you're doing is that you're not talking about the same molecule anymore. Now you're talking about a different molecule. So what you're always doing is you're moving electrons that live in p or pi orbitals. These are the only kinds of electrons that can take part in resonance. Okay, well, so that being said, what you're also doing is that you're moving electrons in unshared pairs. Well, see, what you're actually doing is you move unshared pairs of electrons, or one bond of a multiple bond system. However you want to think about it, you're moving electrons. An unshared pair of electrons, well, those are two electrons, unshared pairs, but a bond is a shared pair of electrons. A covalent bond is a shared pair of electrons. So when you move around a bond that's part of a multiple bond system, then you are moving electrons anyway. So some of the most typical moves that we see is that we like to use curved arrows. Like to use curved arrows to show the movement. So some of the very common motifs that we will see over and over again is that we have an atom that has an unshared pair of electrons on it, and it's bonded to some atom maybe that looks like that, and we illustrate the motion of the electrons with a curved arrow, right? And so now we have a resonance structure that maybe is going to look like that. See, so what we've done here is we've taken the unshared pair of electrons that lived on X, and now we're saying that that unshared pair of electrons is now a shared pair of electrons that lives in the region of space between X and Y. So that's a very common motif that we see when we write resonance structures. Another common motif would be the movement of one bond of a multiple bond system. So it might be maybe something that looks like this. There's a multiple bond. And now what I'm going to do is I'm going to move that one bond of that multiple bond system. This resonance structure is saying that used to live in the space between X and Y, but now I have given that electron pair to Y. So see how these two resonance structures are sort of like the reverse of each other. Unshared pair becomes covalent bond becomes unshared pair. This is what you're doing when you're writing resonance structures. You're moving unshared pairs, and you're moving one bond of a multiple bond system. Okay, more do's and don'ts about resonance. Looking here for cheat sheet. Where are you? Okay, just bear with me for a second here. You never destroy the octet of the most electronegative elements. The halogens, remember X is just the generic term for halogen. Never destroy the octet of a halogen, of an oxygen, or of a nitrogen, right? An oxygen atom without an octet of electrons, that's okay if you're on the surface of the sun, right? But down here on planet Earth with the rest of us, oxygen is simply too electronegative to lose its octet. Organic chemistry is the chemistry of the compounds of carbon. See how carbon isn't in this list? You can destroy the octet of a carbon atom because carbon is not that electronegative. Another more rules of resonance is that you never exceed the octet of any atom whose atomic number is greater than, never exceed the octet of any atom whose atomic number is less than or equal to 10. Right, so on the periodic table, the atomic number 10, that's neon. So this is saying that hydrogen, carbon, nitrogen, oxygen, fluorine, all of these first and second row elements, you can never exceed the octet. You can never give them more than 8 electrons. Okay, Couple more rules here. Must write formal charges. Remember, the formal charge is never optional. When you're writing resonance structures, you always have to include the formal charges. Okay, a couple more rules here. I'm going to go on to a new sheet of paper. If the molecule is neutral, comma, you can create one new positive charge and one new negative charge, but no more. You can't draw a resonance structure that has of a neutral molecule that has 5 positive charges and 5 negative charges. And the reason for that is that separating positive from negative costs energy. And the higher in energy the resonance structure is, the less likely it is to contribute to the resonance hybrid. So if the molecule is neutral, when you're writing a resonance structure, you can create one new positive and one new negative, period. Okay, couple more rules here. If the molecule is an ion, if there's already a negative charge or a positive charge on there, no new charges are allowed. You can't write a resonance structure that has an arbitrary number of positive charges or negative charges. That's just too high energy a situation. Okay, one more rule. Okay, and so this move here, not allowed if this is the only arrow that you draw in the resonance structure. You can't take a carbon-carbon double bond. And remember, one of the things we're doing when we're writing resonance structures is moving single bonds that belong to multiple bond systems. You can't take that single bond and give the electrons to one carbon or to the other carbon. Not allowed. You can't take a carbon-carbon triple bond and split that bond in such a way that if these are the only arrows that you draw. So if you have more arrows going on in the resonance structures, then this is going to be okay, but this is not a legitimate resonance structure. And the reason for that is because this puts these electrons into those anti-bonding orbitals that we talked about that are high energy and therefore will not contribute to the actual structure of the molecule. Okay, I'm going to take a 10-minute break now, and I will hang around to answer any questions on the chat if I'm able to do so. And then let's synchronize our watches. So this says 9:54. So let's say at 10:05, we'll be back for more. Okay, so trying to deal with some of these questions on the chat. Could you put the previous page up? All of those rules, this one? With the example of X to Y to show movement, why is that possible, but the carbon-to-carbon arrow movement is not allowed? Because, see, if I had, so if I had a carbon-oxygen double bond, it would be okay to give the electrons to oxygen. But if it's a carbon-carbon double bond, it's not okay to split those bonds up because the electrons are put into antibonding orbitals, if that's the only thing we do. What would be the hybridization of a carbon quadruple bond? I don't know. That's not organic chemistry. How often do molecules have resonance? How do you know? Well, trial and error procedure. Resonance is very, very common. Okay, anything else? All right, so I'm going to go have a sip of coffee. Oh, for the last rule, is that specific to just carbon? Yes. If I had a carbon oxygen double bond, I can shift the electrons to one side or to the other, but never for a carbon carbon double bond or a carbon carbon triple bond. Okay, so a lot of this will become, yeah, a sulfur-sulfur double bond. That's not organic chemistry. So I don't have no idea about a sulfur-sulfur double bond. Okay, I'll be back.
Okay, hi once again. So I gave you a bunch of rules for writing uh, resonance structures. So the best way to learn about those rules is just to practice them. The most common, the most stereotypical move in organic chemistry as far as resonance structures is concerned is the charge separation of the carbon oxygen double bond. So this is something that we're going to just see repeatedly over and over and over again. This is the most important and the most common move in all of resonance. So we have the carbon oxygen double bond, and we want to write a resonance structure for that. Okay, so uh, what I see is I'm moving unshared electron pairs, and I'm also moving single bonds that belong to multiple bond systems. So even though I never have to write an unshared pair of electrons, I'll just go ahead and write the unshared pairs of electrons on this oxygen. And I see that this is a double bond system. One of the things I can do when I'm writing resonance structures is move a single bond, move one bond that belongs to a multiple bond system. So what I'm going to do is I'm going to take these electrons that live in the region of space between the carbon and the oxygen atom, and I'm going to give them, move them up, showing the movement of the electrons with that curved arrow. I'm going to move them up to that carbon. To the oxygen. That double bond has become a single bond. And this oxygen atom, it started life with two unshared pairs of electrons. Now it has three unshared pairs of electrons. Where did the third unshared pair of electron come from? Well, it used to live between carbon and oxygen, and now it lives on the oxygen. Okay, so now, but I'm not finished with this resonance structure yet because I always have to take care of formal charges. And last time I gave a prescription about how to calculate a formal charge based on group number and so on. So this carbon is group 4. 4 minus 3 bonds is 1. 1 minus 0 unshared pairs of electrons is still 1. So this carbon must have a positive 1 formal charge. Okay, this oxygen, he's group 6. 6 minus 1 bond is 5. 5 minus 6 unshared electrons is negative 1. This oxygen must have a negative 1 formal charge. Okay, so there's our first resonance structure. But remember, what resonance structure is saying is that the actual structure of the molecule never looks like this, never looks like that. This is the horse, this is the donkey, but the actual structure of the molecule is a composite of its resonance structures. So that is not really a carbon-oxygen double bond. It's somewhere between being a single bond and a double bond. And this carbon really isn't neutral. It has a partial positive charge on it. And this oxygen up here isn't really neutral either. It has a partial negative charge on it. So that is the actual structure of the molecule. It's this resonance hybrid. So this is the most important resonance structure in organic chemistry. Okay, so now let's do this problem again, but now let's do it wrong. All right, so I was able to scoot this electron pair up to this oxygen. Now I'm going to try to scoot it down to the carbon. Resonance question, right? I'm doing this wrong. So this carbon had 0 unshared pairs of electrons. Now it has 1. Where did that unshared pair come from? It used to live between carbon and oxygen, but now I've given it to carbon. This oxygen used to have two unshared pairs of electrons. I didn't diddle with those, so it still has two. This is totally wrong. Why? Tell me in the chat. What is so terribly wrong with this resonance structure? Oh, oxygen doesn't have an octet. For one thing, right? I destroyed the octet of this oxygen atom. Another thing that's wrong with this resonance structure is that I haven't written the formal charges. So oxygen is group 6, 6 minus 1 bond is 5, 5 minus 4 unshared electrons. This oxygen should be positive. Carbon is group 4, 4 minus 3 bonds is 1, 1 minus 2 unshared electrons is -1. Even if I write the formal charges, it's still wrong. Why? I've destroyed the octet of oxygen. Not allowed. No octet. Okay, so now let's just practice writing some more resonance structures. What if I were to ask you to write a resonance structure for nitrosyl fluoride, FNO? Okay, so maybe we can write in all of the unshared pairs of electrons. Maybe we can write all of these unshared pairs of electrons. When we're moving unshared electron, when we're writing resonance structures, we're moving single bonds that belong to multiple bond systems, and we're moving unshared pairs of electrons. So going to do this problem wrong a couple of ways and then see what's wrong with each of these moves and then fix it. Okay, here's an unshared pair of electrons. I'm going to move it there. Resonance question. Okay, so this fluorine would be now positive. This nitrogen would be negative. What's so terribly wrong here? Tell me in the chat. I exceeded the octet of the nitrogen, right? Nitrogen is in that first and second row of the periodic table. So this nitrogen now has 10 electrons. That's wrong, right? Too many electrons, more than 8 electrons. I've exceeded the octet. So that's no good. Okay, so let's do this problem wrong another way, trying to show what would be the most common mistakes that people make. I can move unshared pair, I can move single bonds that belong to multiple bond systems. So what about something like this? What would be so terribly wrong here? See how that nitrogen has started out with 1 unshared pair of electrons. Now it has 2. So what's wrong here? Well, once again, this nitrogen, I've exceeded the octet of the nitrogen. And this would also have a, something's wrong. Oh yeah, this should be a single bond. Sorry about that. That should be a single bond. This should be positive and this should be minus. Okay, so all of that's wrong. So now let's fix it. So what would be a legitimate structure here is that I can move this electron pair here, but I can't stop there because if I do, I'll end up with a nitrogen atom with too many electrons. Can I fix it? Yes, by chasing away this single bond that belongs to this multiple bond system. I can do something like that. See, so now these are 2 arrows. So that becomes this. Now, this fluorine atom, I could calculate its formal charge using the group number minus the number of bonds minus the number of unshared electrons. I could do that. But a more common sense way of doing this would be to note the following. This fluorine is neutral. This arrow means I'm pushing electrons away from something that is neutral. An electron is negative. When you push electrons away from something that's negative, that thing is going to pop out positive. I could calculate the formal charge of this oxygen using the group number minus the number of bonds minus the number of unshared electrons. But the more common sense way to look at it would be this oxygen is neutral. This arrow means I'm pushing electrons towards something that's neutral. Electrons are negative. If I bring something that's negative to something that's neutral, that oxygen is going to pop out negative. This nitrogen in the middle, he's neutral. This arrow means I'm pushing electrons toward it. This arrow means I'm pushing away from it. So he doesn't experience any net change in his formal charge. So that's a legitimate resonance structure. I haven't broken any of the rules. That fluorine has an octet. This nitrogen has an octet. This oxygen has an octet. I started out with something that's neutral and I created one new positive and one new negative. That's fine. The actual structure of this molecule is that's not a single bond between fluorine and nitrogen. It's somewhere in between being a double bond and a single bond. That's not a double bond between oxygen and nitrogen either. It's somewhere in between being a double bond and a single bond. This fluorine isn't really neutral. It has partial positive charge. This oxygen isn't really neutral. It has partial negative charge. So this is the resonance hybrid. And it's important to remember that this molecule, FNO, nitrosyl fluoride, never looks like this. It never looks like this. This is the horse. This is the donkey. It's not flipping back and forth between looking like this and looking like this one instant, then looking like that. It's not flipping back and forth. It never looks like that, never looks like that. These are not accurate descriptions of the bonding, ever. The actual bonding is given by this composite. Okay, so let's practice writing some more resonance structures. All right, so this is the molecule called biacetyl. It is the molecule that is responsible for the delightful flavor and aroma of butterscotch. This has the carbon-oxygen double bond. We said that the most stereotypical move in all of resonance is to charge separate the positive, charge separate the carbon-oxygen double bond. So there's a legitimate resonance structure. But now here's another carbonyl. There's another carbon-oxygen double bond, and I like to charge separate a carbon-oxygen double bond a lot, right? And so I'm going to come up with this other resonance structure, but this one is terribly wrong. What's wrong? Tell me in the chat. Does it matter if F is more electronegative than no? No, it doesn't. What's wrong with this resonance structure here? Right? I charge separate the carbon-oxygen double bond. I did it once, I did it again. What's so terribly wrong with this? Too many charges. Look at this rule. If the molecule is neutral, you can create one new positive and one new negative, period. Right, that's it. What I've done here in this incorrect resonance structure is to come up with a molecule that has more than one positive charge, more than one negative charge. And the reason that this is not acceptable is because the energy of this molecule is extremely high. Positive hates positive. Positive loves negative. And so here, what I'm saying is that the actual structure of the molecule has these two positive charges jammed up next to each other. And that is just a too high energy situation. When the molecule is neutral, you can create one new positive and one new negative. This one's no good. But I can return to this one, and now I'm going to fix it. I'm going to take the electron pair on this oxygen and restore the original double bond. Then I'm going to chase away the other double bond. Now I've come up with a resonance structure that has one new positive and one new negative. That's a legitimate resonance structure. So by restoring the original carbon-oxygen double bond, now I have this other legitimate resonance structure. And what is the actual structure of the molecule? The actual structure, what does the resonance hybrid look like? Well, I came up with a resonance structure where that wasn't a single bond. I came up with a resonance structure where this wasn't a single bond either. Oxygen here, partial negative, partial positive, partial positive, partial negative. So that's the resonance hybrid. It looks like it maybe came from this, but it didn't. Okay, so are we getting the hang of it? All right, so how about let's continue practicing. What about this guy here? What if I were to say, draw two resonance structures? Okay, so I'll let you play with that, and then we will divulge the answer. All right, so here's that carbon-oxygen double bond that we see so frequently. So one resonance structure that we see a lot would be the charge separation of that carbon-oxygen double bond to make something like that. Okay, now what? I need another resonance structure. What am I going to do? Tell me in the chat. What do I do now? Anybody have a suggestion? Move the electron pair on the nitrogen. Exactly. That's exactly what I need to do, because there's an electron pair here. And like I said before, is that I never have to write an unshared pair of electrons. You need to know if there are any there and how many there are there. So there's an unshared pair of electrons on this nitrogen. When I'm writing resonance structures, I can move unshared pairs, and I can move single bonds that belong to multiple bond systems. So my next resonance structure could be where I'm taking that unshared pair of electrons, they're negative, negative loves positive. This makes total sense that a negatively charged unshared pair of electrons would be attracted to a positive charge. And so I have a new resonance structure where now I've created a double bond between the carbon and the nitrogen. And I always have to make sure to take care of the formal charges, right? So this nitrogen was neutral. This arrow means I'm pushing electrons away from something that's neutral. It's going to pop out positive because electrons are negative. And if I take electrons away from something that's negative, it's going to pop out positive. This carbon was positive. This arrow means I'm pushing electrons, negative electrons, to something that's positive. It's going to pop out neutral. So these are the three resonance structures for this molecule, and the resonance hybrid, the actual structure of the molecule would look something like this. That's not really a double bond. That's not really a single bond. There's partial negative there, there's partial positive there, and there's partial positive on the carbon. So there's a lot going on in this resonance structure. So how we do it? Getting the hang of it? Yes? All right, so let's just try more and more and more and more examples. Okay, how about draw a resonance structure? Sit down here. Okay, so this oxygen here, I don't have any multiple bonds, so the only thing I can do here is move unshared pairs of electrons. So what if I took this oxygen? What if I did that? This would be positive, this would be negative. How's that look? Is that good? Oh, no, that's not good. I didn't break the octet of the oxygen, but I exceeded the octet of the nitrogen. No good. All right, so maybe the answer is to move the unshared pair on the nitrogen. Maybe do that. This nitrogen would pop out positive, this oxygen would pop out negative. How's that look? No, I've exceeded the octet of the oxygen, not allowed. This molecule doesn't have any resonance structures. So that this is really a single bond, that's really a single bond, that's really a single bond, that's really a single bond, right? So not every molecule is going to have resonance structures associated with it. Okay. So now, are you ready for something really hard? Are you ready for something really hard? Okay. What if I were to say, draw 5 additional resonance structures? Right? Up to now, we've just been piddling around with 1 or 2 resonance structures, but some molecules have many, many resonance structures. So let's try to come up with 5 resonance structures for this. Okay, who wants to start us off? I do. Well, there's that carbon-oxygen double bond. I know that that carbon-oxygen double bonds, the separation of that charge separation of that carbon-oxygen double bond, that is the most stereotypical move in all of resonance. So there's our first resonance structure. 1 down, 4 to go. Okay, what do I do next? Tell me in the chat. Oh, yeah, move the lone pair on the nitrogen. We just did that in the previous resonance structure. This nitrogen has a lone pair of electrons. I can slam this unshared pair down. And so now I have this guy. And always taking care of my formal charges, right? Without the formal charge, the structure is just wrong. This nitrogen was neutral. I'm pushing electrons away from it. It pops out positive. This carbon was positive. I'm bringing electrons toward it. It's going to pop out neutral. Okay, 2 down, 3 to go. Now what? Tell me in the chat. What am I doing next? Okay, someone is saying double bonded oxygen can be moved, but am I going to draw an arrow here and leave everything as it is and just have a new positive here and a new negative here? Oh no, I'm not going to do that, because then I'm going to have more than one. The structure is neutral. I can create one new positive and one new negative, but not more than that. So yeah, I can charge separate this carbon oxygen double bond down here at 4 o'clock, but I have to restore the carbon oxygen double bond up there at 12 o'clock. So bring this unshared pair of electrons down like that. That restores that carbon oxygen double bond, but I can't stop there, because if I stop there, I'm going to have a carbon with 5 bonds, and that's no good. So I'm going to chase this single bond and put him back on nitrogen. All I'm doing is trying to get back to this configuration over here. And now, but only now, finally and at last, can I charge separate the carbon oxygen double bond down there at 4 o'clock. So I restored the top of this molecule, and now I have diddled with the carbon oxygen double bond down there at 6 o'clock. So there's my next resonance structure, right? If the original structure was neutral, I can create one new positive and one new negative. Okay, 1, 2, 3 down, 2 to go. Now what? Any suggestions? What do I do? Yeah, now it's time to start diddling around with the unshared pair of electrons on this oxygen. Right, this oxygen has an unshared pair of electrons. I could do that. So now there's my next resonance structures. Okay, 4 down, 1 to go. Now what? Any suggestions? You know, one of the tips, one of the tips and one of the tricks that I can share with you about writing resonance structures is that there is no order of writing resonance structures. You can revisit any previous resonance structure and draw a new resonance structure therefrom. So unless you're an expert, you don't have to write the next resonance structure from the last one that you just wrote. That's always possible to do that, to draw the next resonance structure from the last one you wrote, but that is not required. You can go back to any previous resonance structure and draw a new resonance structure from it. So what I'm going to do is I'm going to go back to my original. I'm going to go back to my original and I'm going to come up with another resonance structure from the original. Right? You don't have to write the next resonance structure from the last one you just wrote. That is always possible, but it's not necessary. So now I want to get this double bond into play here. So one of the things that I could do is move this single bond of this multiple bond system. And then I can't stop there. I have to chase away one of the bonds of the carbon oxygen double bond, or else I'm going to exceed the octet of carbon. So there's another resonance structure. Oxygen is negative. I have a double bond there, and carbon here is positive. Notice I've destroyed the octet of carbon, but that's okay because carbon is not an electronegative element. Oxygen, fluorine, nitrogen, these are very electronegative elements. You can't take away their octet. But carbon isn't electronegative, so we destroy the octet of carbon all the time. We did it up here. 1, 2, 3, 4, 5. Okay, so there I see 5 resonance structures. Can we come up with another one? Can we come up with another one? What am I going to do? Any suggestions? So what am I doing? Okay. So I could do a lot of things, but I know that this oxygen has an unshared pair of electrons on it, right? I could move the electron pairs over here. So yeah, I've come up with another resonance structure that I haven't had already, and that's going to be this one. Oops. Right, so this molecule has lots and lots of resonance structures. I'm sure there are others that, and maybe just for fun, you can come up with some additional resonance structures of your own. So getting the hang of it. Okay, so now let's talk about some special cases with resonance. This is probably something that you've already seen maybe in Gen Chem. Do you guys know about benzene? Right, so we have benzene that looks like this, and maybe you've seen this resonance structure, right, where we're just moving all of these double bonds. All right, so maybe you've seen that somewhere in Gen Chem, that you're moving this double bond, but you can't stop there, because if you do, you're going to end up with a carbon with 5 bonds, and so you have to chase away, and you can't stop there. You chase away. So this is another resonance structure that we see quite a bit. Okay, so now let's return to the issue of predicting hybridization. Now that we know about resonance, I want to talk about some of the consequences of resonance. Consequences of resonance. So the one that we have maybe alluded to earlier in the lecture would be this modification of hybridization state. So let's go back to nitrosyl fluoride. give me the hybridization state. What is the hybridization state of the fluorine? Okay, so this fluorine, its steric number is equal to 4, right? And our rule for predicting hybridization is that it's steric number -1, unless the atom has an unshared pair of electrons that can be moved around in resonance. And in that case, the hybridization state is going to be Sn-2. So this is steric number of 4. Does that mean sp3 hybridization? It does not, because this fluorine has an unshared pair of electrons that can be moved around in resonance, right? So it's not sp3, it's sp2. It's steric number -2. So this is one of the consequences of resonance, is that it will alter the prediction of hybridization based on the steric number concept. Okay, so what's the hybridization state of this oxygen? Oh, okay. Before we do that, let's go back to this. Okay, so now what is the hybridization, what's the steric number of this fluorine atom in this resonance structure? Its steric number is 3, right? And so what would be the prediction of its hybridization state? It would be sp2. Question: unless the atom has an unshared pair of electrons on it that can be moved around in resonance. So can I do this? Can I do that? Question: can I do this? Oh, absolutely not, because I've broken a couple of rules of resonance, right? That nitrogen atom, this nitrogen atom, now there's an unshared pair of electrons on it, If the octet has been exceeded, that's no good. So see, this resonance structure is saying steric number 3 for the fluorine, and it's predicting sp2 hybridization. Unless there's an unshared pair of electrons on it, then I can move around in resonance. But this fluorine doesn't have an unshared pair of electrons on it that I can move around in resonance. So the hybridization prediction is correct. And that's exactly what we got in this earlier example. It's sp2 staying sp2. It's not sp3 changing over to sp2 and then back to sp3. It's never sp3. It was sp2 all the time, all the time. Okay, so let's go for some of these other atoms in nitrosyl fluoride. What's the hybridization state of the nitrogen? What's the hybridization state of the nitrogen? What's the steric number of the nitrogen? Steric number is equal to 3. So we're saying sp2 maybe, unless there's an unshared pair of electrons on it that can be moved around in resonance. So can I move that unshared pair of electrons around in resonance? Can I do this? Question: no, I've exceeded the octet of the oxygen. Can I move it in the other direction? Can I move this unshared pair of electrons in the other direction? No, I can't do that either. So this nitrogen atom has an unshared pair of electrons on it, but it cannot be moved around in resonance. The steric number prediction is correct, sp2. Right? You get it? How about let's go for the oxygen atom in nitrosyl fluoride? What's its hybridization state? Steric number? Equal to 3. So is that sp2? Does it have an unshared pair of electrons that I can move around in resonance? How's that grab you? Oh, that's not very good. I've exceeded the octet of the nitrogen. No, so that didn't work out. I'm going to do it over here. What about this chasing away business? Right? I saw that that was my salvation in an earlier problem. Maybe the answer is to move this guy here and chase this guy away like that. Maybe that's the answer to the problem, is it? Oh my God. Oh my Lord, this is so hideous. Ugh. Broken a couple of different rules of resonance, right? That's no good either. So this oxygen has unshared pairs of electrons on it, but they cannot be moved around in resonance. So the steric number prediction holds. Okay, so just to summarize, in this nitrosyl fluoride, we have the fluorine atom is sp2, the nitrogen atom is sp2, and the oxygen atom is sp2. What is the shape of nitrosyl fluoride? Right over here, I'm just gonna, instead of going to another sheet of paper, what we've just seen is that this is sp2, this is sp2, this is sp2. What if I wanted to draw a picture of this molecule using solid lines, dashing, and wedging? Fluorine to nitrogen to oxygen. Right? It's a bent. The molecule is bent. It's not linear. Okay. So how's it going out there? Well, I hope. Let's try some more. Tell me the hybridization state of everything. So what about this oxygen? What's its hybridization state? Steric number 1, 2, 3. sp2 question. Does it have an unshared pair of electrons that I can move around in a legitimate resonance structure? Can I do this? Well, that I didn't exceed the octet of the oxygen. I didn't break its octet. I didn't exceed the octet of carbon. That looks perfectly okay. So it's not sp2, it's sp. And now what would be the hybridization state of this oxygen over here? It's also sp. This is a steric number of 2. And there's an unshared pair of electrons on there, but I can't move them around in resonance. So the steric number prediction holds. So, oh, sorry, sp. So this oxygen is never sp2, right? It's not flipping back and forth between being sp2 and sp. It's just always sp. What's the hybridization state of the carbon? What's the hybridization state of this carbon? Think it's going to be sp, right? Steric number of 2. Is there an unshared pair of electrons on there? Well, writing electron pairs is optional. Have I just been like tricky? Is there really an unshared pair of electrons on there that I never wrote? No. So no unshared pair of electrons. It's sp hybridized. Okay. So this is how, so we started out the lecture talking about hybridization and about how resonance modifies the prediction of hybridization. Resonance also has other consequences, but I don't want to, I would rather wait until next week to talk about the further consequences of resonance. And so, well, let's see. So I think maybe we'll end it there, but let me tell you that next Thursday we have our first quiz. Over the weekend, I will be publishing a study guide for the quiz. It's going to include all of the material that we've talked about and including stuff on Tuesday, because Monday's a holiday. Stuff on Tuesday will be on the quiz, and that is going to be about the functional groups. So I'll publish a study guide about the quiz, but if you want to work on this over the weekend, so let me just make a preliminary study guide here for quiz 1, and that will be all of those issues dealing with bonding, hybridization, writing resonance structures, the bond line, condensed, and Lewis formulations, resonance, and also its consequences. And then on Tuesday, I'm going to start talking about the functional groups. And so that's what I'm planning to have on quiz 1. Okay, so I guess I will hope that you have a very pleasant Memorial Day holiday, and I will now try